Welcome to this session on ISO 26262 with model-based design, a hands-on Simulink tutorial with an X-by-wire example. In this session, we'll explore item definition outlined in Part 3 of the concept phase, using a break-by-wire system as our example throughout the discussion. An item definition is essentially the foundation document for functional safety activities. It's the first formal step in the safety lifecycle from Part 3 of ISO 26262 and defines what exactly you're developing from a functional safety perspective. Think of it as the system passport. It describes the item's boundaries, purpose, environment, and operating conditions, so everyone knows exactly which system is being assessed for safety. Here's a draft of an item definition document for a break-by-wire system, structured according to the guidance in ISO 26262 Part 3 Concept Phase, Clause 5 Item Definition. The first section of an item definition is typically the overview and purpose. This part explains what the item is and how it functions within the larger system. It outlines the key components involved and provides a clear understanding of the item's role. Additionally, it describes the primary objectives the item is designed to achieve, including its intended benefits and overall importance. Shown here is the implementation in Simulink, starting with a single subsystem block named break-by-wire system. The second section of an item definition is the functional description. This part provides a detailed explanation of how the item operates to fulfill its intended purpose. It describes the specific functions and behaviors of the system or component, outlining how it processes inputs, manages internal operations, and produces outputs. The functional description helps clarify the item's role in the overall system and how it interacts with other components to achieve its objectives. To manage specifications in Simulink, first we launch the Requirements Manager app. Open the Requirements Editor. Create a new requirement set named Item Definition. Then define individual requirements by completing key fields such as ID, summary, description, rationale, and any other relevant information. Now that the item definition structure is set up in the Requirements Editor, you can organize and refine the requirements by adding, editing, or grouping them as needed, ensuring each entry contains clear and complete details to support traceability and implementation. The third section of an item definition is the operational scenarios. This section outlines the different conditions and situations in which the item is expected to operate. It covers both normal and degraded modes of operation, as well as potential edge cases. Operational scenarios describe the environmental, functional, and system-level contexts the item may encounter, helping to ensure that its design performance and safety are evaluated across the full range of real-world use cases. The fourth section of an item definition is the system boundaries. This section defines the physical, functional, and logical limits of the item, clarifying what is included within the system and what lies outside its scope. It identifies the interfaces with other systems or components and specifies how data, power, or signals are exchanged across these boundaries. Clearly defining system boundaries helps avoid ambiguity, ensures consistent assumptions, and supports accurate integration and verification activities. Here shows the implementation in Simulink with the corresponding subsystem blocks. The fifth section of an item definition is the interfaces with other systems. This section describes how the item connects and communicates with external systems, components, or subsystems. It specifies the types of interfaces, such as electrical, mechanical, data, or network connections, and the nature of the information, power, or signals exchanged. Clearly defining these interfaces ensures compatibility, facilitates integration, and helps prevent misunderstandings or conflicts during development and testing. Going back the Simulink model, we define high-level interfaces by connecting the relevant subsystems. To provide more clarity, we specify input and output buses for each subsystem, detailing the signals exchanged across these interfaces. We will use the pedal subsystem as an example to demonstrate how to create high-level interfaces in Simulink. In this example, bus element ports are used to define the interfaces, with each bus signal accompanied by a description specifying its purpose and meaning. Now that we achieve a high-level interface that enhances model clarity. The sixth section of an item definition is the assumptions and constraints. This section outlines the conditions presumed to be true during the design and development of the item, as well as the limitations that must be observed. Assumptions may include expected operating conditions, available resources, or user behaviors, while constraints can involve regulatory requirements, physical limitations, performance targets, or compatibility needs. Documenting these factors helps set clear expectations, guides design decisions, and ensures the item remains feasible and compliant within its intended context. The seventh section of an item definition is the legal, standards, guidelines, and best practices. This section identifies the regulatory requirements, industry standards, organizational guidelines, and recognized best practices that the item must comply with or follow. It ensures that the design and development process aligns with applicable laws, safety regulations, quality standards, and proven engineering methods. Including this information helps guarantee compliance, improve reliability, and promote consistency with industry expectations. The eighth section of an item definition is the preliminary safety goals. This section defines the high-level safety objectives that the item must achieve to prevent or mitigate potential hazards. These goals are typically derived from initial hazard analysis and focus on ensuring that unacceptable risks are avoided or reduced to an acceptable level. Documenting preliminary safety goals early in the development process provides a foundation for the functional safety concept and guides subsequent safety requirements and design decisions. The ninth section of an item definition is the functional block diagram. This section provides a visual representation of the item's main functions and their interactions. It illustrates how inputs are processed, how outputs are generated, and how different functional elements within the item relate to one another. A functional block diagram helps convey the system's structure at a high level, supports clear communication among stakeholders, and serves as a reference for both design and safety analysis activities. Taking a closer look at the brake control ECU block, we can develop a detailed functional block diagram that illustrates its internal functions, control logic, and data flow. This in-depth view provides a clearer understanding of how the ECU processes inputs, manages braking strategies and fault handling, and coordinates commands to actuators and other subsystems. This high-level system model in Simulink can serve as an executable specification, enabling early validation of system behavior through simulation. By providing a precise and testable representation of the system's functions and interactions, it facilitates communication among stakeholders and guides subsequent design and development activities. Additionally, adding detailed descriptions and assigning preliminary automotive safety integrity levels, ASIL, to each block in the functional block diagram enhances clarity and safety management. Descriptions help document the purpose and behavior of each function, while preliminary ASIL ratings provide an early assessment of the safety requirements and risk levels associated with each block. The 10th section of an item definition is the environmental conditions. This section specifies the physical and environmental factors under which the item is expected to operate reliably. Defining these conditions helps ensure that the design accommodates real-world operating environments and maintains performance and safety throughout the item's lifecycle. The environmental conditions include vehicle operating conditions such as speed, load, center of gravity, temperature, and other relevant parameters. Additionally, environmental conditions may also include geographic and location-based conditions, such as urban, highway, and mountainous environments. On top of that, external factors such as road surface type, slope, banking, wind, and other relevant surroundings that can affect vehicle performance and system behavior should be taken into account. Moreover, driving maneuvers shall be included to comprehensively address environmental conditions. Furthermore, the behavior of other traffic participants and external actors, including pedestrians and cyclists, should be taken into account. What's more, the presence of vehicle attachments and variations in load conditions must be considered to ensure comprehensive system evaluation. Last but not least, electrical and system conditions, such as power supply dropouts, sensor faults, and network latency, should also be taken into consideration to ensure robust system performance and safety. Once the item definition is complete, we can proceed to allocate requirements to the Simulink model. We begin by opening the requirements created in the previous step. Then, we enable the implementation and verification status indicators, which provide a visual cue for tracking whether each requirement has been implemented in the model and verified through testing. With status tracking enabled, we drag the relevant requirements from the requirements browser and drop them onto the corresponding Simulink subsystems or blocks. When a requirement is successfully linked, the implementation status automatically updates to green, indicating successful allocation. After completing the allocation, we review the traceability matrix to confirm that every requirement has a clear and complete link to its implementation, and where applicable, to associated test cases. Bidirectional traceability, as required by ISO 26262, is to ensure that each requirement can be traced forward to its implementation and test artifacts, and conversely, that each model element and test can be traced back to its originating requirement. Finally, we open the traceability diagram to visualize these relationships, confirming complete coverage and compliance with functional safety standards. To summarize, Simulink provides a comprehensive platform to support the item definition phase. First, it enables effective management, organization, and traceability of requirements throughout the development lifecycle. Furthermore, Simulink helps create detailed functional block diagrams, enabling clear visualization and executable specification of the system's architecture and behavior. By enabling detailed system-level modeling and simulation, it facilitates the item's environmental conditions. Through modeling and simulations, requirements and specifications defined in the item definition can be validated early in the development process, helping to identify potential issues and ensuring consistency. This model-centric approach, leveraging Simulink and the model-based design V model, streamlines the item definition phase of ISO 26262. By providing an integrated workflow, it minimizes development risks and accelerates validation, ultimately enabling the delivery of safer automotive systems. All right, let's wrap up. We have covered what item definition is, explored its key contents, and discussed how Simulink and the model-based design approach can support this phase. I hope this session has given you a solid understanding of these concepts and how they can be applied to support the development of safe and reliable automotive systems. In the next session, we will explore hazard analysis and risk assessment, building on the foundations we've covered today. I look forward to your participation.